Now we're doing finite arithmetic series. By the end of this video, we would have filled in these two blocks with formula. Previously, we had done arithmetic sequences. Now, what we remember with arithmetic sequences is we got a general formula of a plus n minus 1 times d. Now, this is the general formula for any term in the sequence. Now we're dealing with series. What do we know a series is? A series is a sum of a sequence. In this case, we're dealing with only finite arithmetic series, which means there's a determined number of terms in the series. It does not go on forever. Let's just look at some history. Carl Friedrich Gauss discovered a proof when he was only 8 years old. The problem was, how could you add up the numbers from 1 to 100? So he took this general formula where a was 1 and d was 1, making Tn equal to n. And this is obviously all positive integers from 1 to 100. Here, 1, 2, 3, 4, 5. And then you have all positive integers. The sum of n is 1 to 100. And this would give us 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way to 100. What would be a quick way of solving this? How could Gauss solve this extremely quickly without a calculator? Well, let's have a look at this. Let's say the sum of 100, of the first 100 terms, is 1 plus 2 all the way to 100, just like we've written here. Now let's say, what if we put that backwards? So that sum is also equal to 100 plus 99 all the way backwards. What is something we notice here? What is 100 plus 1? 101. What is 99 plus 2? 101. What is 98 plus 3? 101. 98 plus 3 again. 101. All the way till we get 101. Oh, not meant to fill out that 2. What if we add those two together? On the left-hand side of the equation, we get 2 times the sum of 100, and everywhere else we get 101. We also know that there must be 100 of these terms, each equaling 101. So we can simplify that into 101 times 100, because we know that there are n terms. N terms. So we say, that simplifies this greatly. We can say 2 times s, the sum of 100, is equal to 10,100. We can simply divide that by 2, and we get 5,050. Here's an extremely quick way to solve the first 100 digits, add it all up together. And this is what Gauss figured out when he was just 8 years old. Let's have a look at the general formula, the general proof for this. Let's take n equals 1 for any term n ending at term L. Remember, this is the term we are ending at. And this is equal to the sum of n. The sum of n is equal to a, the first term, a plus d, constant difference. Why? Because this is a finite arithmetic sequence. A plus 2d is the next one. And then eventually, as we're getting to the end, it's L minus 2d, L minus d plus L. What if we wrote this backwards? Let's have the L over here, this over here, and we've just written the entire term backwards. Now what do we get if we were to add all these together, just like we did on the previous slide? We're going to get a plus d plus L minus d. The d's cancel each other out. And eventually, we can do that all the way along, and we're going to get, remember the 2 on this side, a plus L plus a plus L plus a plus L, and we know that this is happening for n terms, right here. So we know that there's n a plus L's. Okay, we're getting somewhere. We can now pull this 2 below. We can say 2 divided by n divided by 2 is equal to a plus L. And there, voila, we have our first equation. Something else interesting to note is that L is the same as a plus n minus 1 plus d. Why? This came from our general formula on the previous page. So here we can substitute this L here in for this L over here. And let's see what we get. We get Sn is n over 2, a plus, now we've just substituted a plus n minus 1 times d equals n over 2, 2a plus n minus 1d. And this right here is our second useful formula. Well done. We now have 2 equations to fill in here, and I've simplified it a little bit. We have Sn is n over 2, a plus l, and Sn is n over 2, 2a plus n minus 1 over d. The reason we have the second equation here is we don't often get given this, and we have to work it out. Well done!